Yeah, beginning exactly on time. Okay.
Itala, and thanks for being here. I know that the journeys are very long and we are tired. I will try to be quick in the sense that I will not present perhaps everything that I have here for you, but just like the main central ideas. Until now, we presented this kind of pendulum, the polarities of mathematical thought, and some parts of the pendulum, the analytical pendulum, the synthetical one, and yesterday some kind of mediations between the streams, they going to Hermann Weyl, in part sobre el predicativismo de Hermann Weyl on the Clay library, very recommended. The Phantasmata by Gödel, the doings by De Lorenzo, and the paraconsistency of Da Costa, in the sense that using paraconsistency we can approach this very creative part of the human mind. More than the proof theoretic one, the very creative one, I think is well captured by paraconsistency. So before beginning today, I want to draw two diagrams in which I will try to synthesize many of the tensions that we have seen until now. So the first diagram will be around logic. In which we put at the center of the diagram our master in logic, Kurt Gödel. Gödel should be at the center of our understanding of logic in the 20th century, and as I recall, Gödel is perhaps the best logician and the best intellectual thinker who really understood the three masters before him. Russell, on one side, logicism, the Principia Mathematica produces part of Gödel's work. Hilbert, the formalist tendency in which Gödel will answer two of the main problems of Hilbert, the completeness of first-order classical logic and the incompleteness of the Principia Arithmetica and related systems, that is Peano arithmetic, and Brouwer, one of the great masters of thinking in mathematics in the 20th century. I didn't have time enough to go to Brouwer, but you should go to Brouwer as soon as possible, reading directly Brouwer, not just the intuitionistic logic which comes with Gating afterwards, but reading the master. It's extremely interesting. Very beautiful things, and Gödel was the one who captured them very well. Completeness and incompleteness, combining Russell and Hilbert, and the intuitionistic papers by Gödel in the 1930s, and the equiconsistency between classical logic and intuitionistic logic. Around that, something appears that I will call the orotic aura of Gödel. The orotic I remember you that orotic comes from oros, border, frontier. It was really the one who really understood the borders and the frontiers of the different perspectives, the different schools. And that's, for me, the real reason why Gödel is so important, and why we can talk about him as a genius. He's the only one, I think, that really understood in depth the combination of the three perspectives. But he went beyond that. As I was talking yesterday, he had this strange but very profound idea in which, beyond the incompleteness of Peano arithmetic, you should complete our understanding, you should go against our ignorance and complete our world with phantasmata. Phantoms. Those phantoms correspond to an increasing power of formal systems. It's going to be difficult, I think. Okay, but I think it's impossible. No. Right. I think I will have to cry. No. It will be a moment. And afterwards I will go to the toilet. Okay. Don't worry. If you don't hear me, better.
If you became I could ask Luis.
No.
No?
Don't worry.
You must cry.
Yes.
Yeah.
I will try to cry, and if you don't hear me, as I was saying, no problem. You don't have to hear me.
Yes.
Just look at the blackboard, that should be enough. And if you don't see, and if you don't hear, better. We continue in the line of Gödel. Okay? There are phantoms in our world. Those phantoms are captured by something which is called the Yoneda lemma. Yoneda, after Gödel, in which beyond what we can see, which is the representable part of the world, the representable functors, then you have the perceives, which complete the panorama. Those are the phantoms, something which is behind our understanding. And that thing which is behind our understanding is what we may call the inconsistent, but which exists. These are inconsistent objects, but they do exist. We cannot see them. This is a good example. Here we can see only the objects and the representable functors. We cannot see the perceives. But the perceives complete the panorama, and here you get all the limits. Here you get all the limits around the borders. So you are completing and completed the panorama with the tower of increasing formal systems. As a genius, Gödel proved incompleteness, but he didn't believe that. He believed that our systems of actions were not good enough. We had to complete the actions, to complete our understanding of set theory, produce new actions, and with that, with time, understand what was happening in the mathematical world. So this is important because this approaches us to this first idea that inconsistency is fundamental. It's fundamental. Without inconsistency, we will not be close of understanding the world. And inconsistency is related to the abyss. Florensky. But not just Florensky, of course Cantor for Florensky. And of course Gödel, etc., etc., etc. Most of the most important mathematicians and logicians of the 20th century very close to the abyss. Very, very close to the abyss, and something very brave to do. Many of them very close to be completely crazy. Gödel, several times in psychiatric institutes, Cantor in psychiatric institutes, is not strange, because they were going to the deep things, to the depths. So I am very interested in the depths. What is deep? The depth is fundamental, and the depth is related to the abyss and related to being close to the borders and the limits of inconsistency. Okay. So I can here bring an important person. I will bring today several very important critics of the 20th century. The first one is Mikhail Bakhtin. Bakhtin, published here at Unicamp. Beautiful, fantastic text. He's one of the greatest critics of the 20th century, literary critics from the Russian tradition. The Russians go to the really important things, deep things. The depth is a very, very typical effort of the Russian tradition in mathematics. We saw it in philosophy, in logic, first consistent logic. They go to the very important things. They have a special mind. And the school of Russian mathematicians from Florensky, Kolmogorov, Gelfand, whatever you say afterwards, they will be very important next week in the course of teaching. This line of thinking of great probabilists and great topologists at the same time, and great logicians, Silver today, we talked yesterday about Perelman, people who go really to the deep things. For me, the other very beautiful example is Moby Dick, always for me. Like the great example of the great philosophical novel who really went to the really profound things of human life and beyond human life, beyond approaching to the cosmos. So that's my first diagram. I want to make another diagram. I will shout, don't worry, and if you don't hear me, no problem. The other one is about mathematics. Mathematics and logic always go together. I will profit from one example that I mentioned last time, which was Riemann's zeta function. Riemann's zeta function. The zeta function of Riemann is defined over the complex numbers. So it's in the space of continuity. I think I have to, if I want to make my diagram complete, I have to lower that a bit. So we had this idea of Riemann, wonderful, fantastic idea. You introduce complex numbers to understand the discrete numbers. Riemann's zeta, the zeta function over the complex numbers, you are working in the space of the continuum polarity. That is extrapolated to the discrete produced when you, instead of working with the space of the continuum spaces, you pass to the discrete spaces, you appear to work in what I call the Galois finite fields. They are extensions of the numbers CP, and you take extensions with the dimension n, you produce what I call the FPN, the finite Galois extensions. They are discrete constructions invented by Galois when he was 19 years old. And to understand those extensions, FPN, you have to understand what are the curves which lie over these extensions. Here you are trying to understand the curves who lie over the complex plane. You try to understand the curves over the Galois finite groups and the famous Weil conjectures say exactly how do you count points in curves over finite fields. Here you are in the space of the discrete, in fact here finite, and here infinite. This is around 1950. This is around 1860. After the brilliant thesis by Riemann, his PhD thesis of 1851, a very difficult paper, but if in one moment you want to spend some weeks reading a little Riemann to understand two paragraphs, that would be fantastic enough, because that two paragraphs will change your life. I assure you, as a person, not just a mathematician, a logician, as a person, because you are going to the deep things, to the depth. What happened with these Weil conjectures? They were covered by Grothendieck. What Grothendieck was invented were topuses and schemes before, topuses and schemes, in order to solve the Weil conjectures. And he solved them with his students. This is Grothendieck. I will write the Grothendieck in a moment. This is around 1960, 1970. Grothendieck and his major student, and then they proved the Weil conjectures. And how did they do? So the Weil conjectures are something very concrete, coming from a complex idea, and they produce something very big, which solves the conjectures. Well, I want to bring now one question that was presented in one of the courses, not in mine, but in one of the courses, which was a very important question and which wasn't answered. Someone talked about the field with one element. Field with one element. Fields are like the complex numbers, or like the rationals, or like the reals, or like the Galois finite fields. Fields with one element are, in this moment of civilization, impossible to understand. They are inconsistent now. Now they are inconsistent. This moment, they are inconsistent. Why? Because they don't have an analytical definition. There is no analytical definition of the inconsistent word of the field of one element. Nevertheless, it seems to exist. If it does exist, when that will be a construction which is acceptable for analysis and for classical logic theory, we don't know yet. But it is used. It is inconsistent, it exists. And what is more interesting, beautiful, and really, really surprising is that using the inconsistent field with one element, you can construct a cover of this problem, which is called the arithmetic site. Arithmetic site by Allen Kohn, one of the greatest mathematicians of the last 50 years. Kohn was a specialist on C-star algebras. C-star algebras will be mentioned in the course of biology next week. So the arithmetic site is something which now is the first time in the history of mathematics. We have already from 1860 to today, the most important open problem is the Riemann hypothesis. Still today, where are the zeros of the zeta Riemann? I told you that they were expected to lie on the line real number equal 1/2. That's a very important open problem for mathematics, for number theory, for geometry, for statistics, for physics. It goes everywhere. Very, very important problem. It seems that this would be the good connection. Use the arithmetic side in conjunction with this thing which doesn't exist yet. And this could, it is not proved still, but it's the first time in the history of mathematics that there is a structural clear path to prove the Riemann zeta function. First time, very, very important, using something which is at this moment entirely inconsistent. This is interesting and very beautiful for us. Why? Let me continue a little with my crying before I take the microphone. Here we have, in this part, we have a lot of the things that I have been talking about in my last sessions. First of all, the most important probably thing of modern mathematics, the idea of mixture. Mixtures. A fundamental mixture is this one. Is the idea of producing the zeta function in the finite environment. Go from the continuous to the discrete. That mixture was especially studied by, I will put only the initials, and that will remember you perhaps which were the names. Albert Rodman. The mixture studied systematically by Rodman and invented mathematically before him by two of the greatest mathematicians of all times, and certainly two of the greatest mathematicians of the 20th century. On one side, David Hilbert, on the other hand, Henri Poincaré, the greatest mathematicians in 1900. So I put them here. Mathematically, the important ideas are the construction of algebraic topology by Poincaré, Henri Poincaré, the invention of the Hilbert spaces by David Hilbert, and the continuation of those, which will be the Banach spaces. Again, propaganda for multi-discourse next time. Banach spaces. And the one who really understood them from the point of view of philosophy, Albert Lotman, is the one who really captured the idea of literature. That's one of the important parts of the perspectives. The other ones are those who are related to this kind of big panoramas. These big panoramas are what we call here the horizon. You have to have a horizon in order to get some kind of covering of mathematics. Those horizons are presented by the Santilli, Rambus and the Santilli. And also by these ideals where mathematics is tending to. Those ideals were very well presented by this unknown, very important Ohio professor, James Byrne Shaw. Ideas. Other things that we saw, let me check a little my picture, I don't want to forget the basic important things, were at the left, at the right, when we are talking about continuity, we are talking about topology. So we are talking about angels. Here are the angels. By Hermann Weil. I will not put them here, the devils. Okay. This is very important. The inconsistency is a blind point, something which we cannot see. It's a blind point. Very, very important to have blind points. If you have only clearness, you are not seeing anything. That's a very polemic issue. If you think that you are seeing something clear, then you are not seeing. Why? Because you are not seeing what's important, what is hidden, the deep things, the depth. That's the important part. The blind points are the important parts, or what we call there the abyss. And this is Châtelet, or the abyss, with the great Cantor and company. We have here Cantor, we have Russell. Many of the most important people that we talk in this week are here. Cantor, Russell, when Russell defines mathematics as the thing which we cannot talk about. Of course, Newton, Da Costa, Paweł Florensky. Paweł Florensky, our master in these are essentially the ones that I wanted to put here. Yes, there is another thing, to go against the currents, what they called recalcitrant mathematics. To resist against all currents. That's better. So you see that in this diagram, all of the people that we talked in the week are there. In a small, very synthetic diagram with a very precise problem. problem of how is happening the Riemann zeta function in the finite reality. When you change, you produce great mathematics. And in fact, we are now in this situation. We come back a little backward. Here, in this first very intuitive diagrams of my hand, you have all the basic polarities, and they are all there. The polarity between space and number, the polarity between the negative and positive, the one and the many, the continuous and the discrete. What is beautiful is the important part. I should write it down. I will put it now. The abstract, very abstract horizons and the concrete horizons, the infinite and the finite, the possible and the necessary, and the structure and its deformation. They are all there. I will stress that here in the middle, we have the important thing. The important thing in the middle is this. You have to accept that this is the important thing. The heart of mathematics. The very heart of mathematics is beauty. If there is no beauty, there is no mathematics. Forget about mathematics if they are not beautiful. That's the real work. Yes? Cons lives and is one of the greatest mathematicians still living. Yes. It's a very good for us that Cons still lives and that he has still the goal to prove that. But it's an extremely difficult question. It has advanced a lot, and age doesn't always help. He's already 80 years old, so he's very vigorous and very intelligent still today, but it's difficult. Probably some of his students will be able to do that, as happened with Grothendieck and Deligne. So this very intuitive and at the beginning I imagine for you seemed very naive. Play with hands is not so naive, and in there you have a good approach to the difficulty and richness of mathematics, as we have seen in the previous sessions. Let me show you a quote by this man, Bakhtin, important literary critic, that we should follow more or less with very much care. A beautiful quote by Bakhtin, 1924. On the line of the Russian people, they go to the deep things. They don't stay on stupid surfaces. They go to the really important things. Bakhtin, every cultural act lives essentially on the boundaries, and it derives its seriousness and significance from this fact. Abstracted from these boundaries, it loses the ground of its being and becomes vacuous, arrogant, degenerates, and dies. Wow, that's the point. That's the point. You have to live in the borders. You have to live in the frontiers. Especially if you are young people, you have to go against the currents, against the dogmas, against your professor, as I will show in a moment. That's something fundamental. Do never believe in your professor and your teacher. Never, never go against him or her constantly. You have to go really beyond. If not, you will become vacuous, arrogant, and degenerate. I don't want to recall what is the degenerate for me in the philosophy of mathematics. It's the Oxford philosophy of what? The generation of thought. Very interesting, but never call it philosophy of mathematics, call it, as I said several times, the last time that I say it, the Oxford Handbook of Self-Reference Anglo-Saxon Secondary Literature on Classical and Standard Logic. Okay. If you go to the borders, then you will be near the abyss. You will be near the Costa. Yes, that's the man. That's the man to follow. That's why I hope that next week also Itala will repeat the film on the Costa, because you have to see it, and we have to see it again and again and again, because he's the master. He's the master, and he's saying the important things. So finally, let's come back to my session of today. So I will mostly skip this session. I think that the two diagrams are the most important things. But I will be brief in the sense that let me do in 45 minutes, say, these other perspectives. These are perspectives that I have provided on the philosophy of mathematics in the last 10 years. There are two main alternatives. One is the construction of something which, after being able to capture the diversity, the analytical diversity, the synthetic diversity, the medium diversity of the pendulum, after allowing the diversity, we try to get some unity again. Is it possible? Yes, I think it is possible. And I will show you how. That's the first idea. Use some techniques of mathematics in order to produce, again, the unity behind the diversity, or to produce some integrality beyond the differences. In a more general sense, to produce a differential and integral calculus for today in a very abstract sense. Very, very abstract sense, but which can encompass many things of mathematics, many things of logic, many things of culture in general, not just mathematics and logic. We are part of a much more interesting cultural world in which mathematics is something very interesting, very beautiful. I love and adore mathematics, and logic is very, very small. I love and adore logic, but there is something much bigger, which is culture, which is very, very important, much more important than the things that we do. So it's important that they come here in the panorama. I will talk about that. The first part, I will use sheaves and toposes to produce the unity. And in the second part, I will try to show you that something like mathematical criticism should be done. We know very well what is literary criticism. There are constructions, literature, novels, stories, poetry, and then there is literary critic who looks at the different outputs of literature and produces an understanding of literature. That's clear in literature. It's clear in art. You have a lot of different constructions of art, and the art critic is the one who permits to understand what is happening in the art world. It is clear in music. You have all the different constructions of music. The music critic will be able to help us to understand what is happening in those scores and in those interpretations. It is clear in film theory. You have the films, and then you have the film critic, which is fundamental to understand what is happening in film, etc. It doesn't happen in mathematics. Why? It's completely crazy. But it has happened until now. There is no mathematical criticism. And there is something which is called the philosophy of mathematics. Those things are completely different. You can do beautiful philosophy of mathematics without, most of the time, even understanding what is happening in mathematics. But in mathematical criticism, you will never be able to do that, because you have to look at the mathematics. If you look at the mathematics, then you will have to produce an effort to understand what is happening there. there should be then a mathematical criticism. I will show you how this is beginning to be done. So first of all, 2 or 3 simple ideas. The first one, which is also related to part of this diagram. In this diagram, we have several levels over there. I will write them down explicitly. In this diagram, you have the level of what is happening here, the phenomena. So there is a phenomenology that must be understood. What are the phenomena of mathematics? Fundamental strata, the strata of phenomenology. Behind the phenomena, there are something very strange, which are the phantoms, or what I will call the archetypes. So there is some kind of metaphysics behind. And then there is the movement of mathematics, the history of mathematics, which is really, really fundamental. You cannot, I say, you cannot understand mathematics without its history. It's fundamental to go through courses of the history of mathematics to try to understand a little of mathematics. The history of mathematics is fundamental. If not, you will never understand. You have to go to the history of mathematics, how concepts have evolved, etc. This was stressed yesterday by Valerie. It was very nice to see a young person interested in history, not just old persons like us, no. Young person interested in history, in the development of our thought. So history, phenomenology, and metaphysics should appear. Afterwards, after these levels have appeared, they have to go beyond the borders. So there should be here ramifications to the cultural understanding. Here you have 4 levels. The level of history, the level of phenomenology, the level of metaphysics, and the level of culture. They can be integrated together. Very easy. Very easy. This is why I will show you with a very, very simple model. So, first of all then, recalling this concept that I consider still one of the most important inventions of mathematics in the 20th century, and possibly all the times in mathematics. The sheaf, the idea of sheaf. The sheaf is very, very simple. I have presented it before, but I will present it again here with a little more care. What is a sheaf? It's just 2 topological spaces, one on the bottom, one on the top. The one on the bottom can be understood as a folding of the upper space, and the upper space can be understood as the unfolding of the bottom space. So the upper space has more information than the one which is on the bottom, and it is unfolded over the bottom. So technically, it's just 2 topological spaces with a projection from the bigger space to the lower space. That's a sheaf. There is another more technical definition. I will mention it very briefly. You need that projection has good topological properties. Since we are talking about topologies, that projection should have a good topological property. I will mention it in a moment, but for the moment it's just 2 topological spaces, one on the top and one on the bottom, the one folded, the upper unfolded. Take that idea and produce this reading. This is my first basic reading. How to understand the connection between philosophy and mathematics. Mathematics should be on the bottom. Mathematics is the world of definitions, theorems, examples, proofs, etc. That's what we call usually mathematics. But beyond that, extremely important, it was mentioned yesterday, thanks to one of the questions, beyond that, there is an informal rigor where imagination develops. That imagination is fundamental. Without imagination, the proofs doesn't make sense. The imagination without proof doesn't make sense. Both of them are fundamental. So on top of definitions and theorems and examples on the fiber, you have notions or ideas, and then you connect the different notions or ideas, and that produces you some kind of methods or theorems or good mathematics. So the back and forth between the technical and the philosophical is fundamental for mathematics, and that can be modeled with this simple idea that the mathematical thought in a good sense, is at the same time mathematics and philosophy, at the same time technique and ideas, at the same time proof and imagination. Those things are fundamental. And this can be captured very well over any definition, any theorem. There should be an idea. And always there is. A good mathematician or a good teacher, perhaps not a good mathematician, but a good teacher, should be able always, when he or she produces a definition or a proof, to show to the student what are the ideas behind the proofs, what are the examples, what is the basic intuition. It doesn't happen. And that's the problem with mathematics often. It is very badly taught. And it is just taught as a sequence of theorems, sequence of proofs. That's horrible, it doesn't make sense. Mathematics is something much more complex, much more complicated, where intuition, as Poincaré insisted, was fundamental, images are fundamental, horizons are fundamental, blind points are fundamental, and also all the positive part of proofs, theorems, examples, etc. This is captured very well with the shift, with the mathematical thought as a shift. Mathematics is not a technique on the bottom part. It is not a language. It is much more than that. To reduce mathematics to a language is one of the horrible things of the 20th century. If you go with this idea, then you can begin to understand a little more that these concepts, ideas, and dialectics, which are living on the imaginary space, we were talking yesterday about the importance of the complex numbers, the imaginary space, the space of imagination, that the space of imagination incarnates in real definitions, theorems, proofs, back and forth between the vague and the architectonic construction. It's interesting, I was producing yesterday the hypothesis that this upper space has a logic which is paraconsistent in a very neat sense. Instead, on the bottom space, you have the usual subintuitionistic logics. If you go back and forth between the upper space and the bottom space, and you take that projection to have some properties, which are the topological properties, which are precise in a technical sense, we could get some of the most important dreams in the history of the philosophy of mathematics. The first one, which is interesting and good for the teaching of mathematics, is that the fibers are non-empty. Ideas always exist beyond techniques, and mathematics is a form of thought. So if you teach or you have been taught mathematics as a technique, you are losing a lot, and you are not understanding mathematics, and finally, you are hating mathematics, because mathematics is not a collection of proof techniques. It doesn't make any sense. The other thing which is important is that this projection is continuous. If it is continuous, it is open. So it will be always open to new understandings. You will never be closed in mathematics. It is open to imagination, to new things. And here, some of the two basic dreams in the philosophy of mathematics. Leibniz dream, an idea in a fiber can be bounded enough in the upper space so that its technical folding captures fully its philosophical ground. So in one famous page, Leibniz said, let's don't talk, let's calculate. Okay, that's the idea, the Leibniz dream, that the ideas can be captured well enough that in the bottom space you can do calculations and understand what is happening in the upper space. And the other way around, that I call Peirce's dream. Mathematical symbols are enough rich to capture fully the unfolding differences between concepts and ideas. Peirce, as you know, was one of the founders of modern semiotics. We will come back to Peirce in a moment afterwards. So this is the first simple, but I think useful idea. Mathematical thought, not mathematics, mathematical thought can be understood as a shift, with at least the layer of technical mathematics in the way of definitions, proofs, examples, theorems, what we call usually mathematics in the bottom space, but with this other space, the space of imagination, which is projected onto the usual techniques. But the problem with this first model is that it is a static model. The shift is there. The shift helps to understand the phenomenology of my diagram, but it doesn't take care of history. So we have to move things. Second stage is begin to move things. Mathematics has several layers. In one of these layers, for example, in this one, you have one of the shifts in which you have an environment of mathematics and the ideas on the top. The connections between the ideas are the sections. And what we are looking is to find enough sections to understand mathematics. If we understand them locally, then we will have local understanding. But if we are able to glue the different local understandings, then we are beginning perhaps to understand a little more of the most important problems. But this is just a part, one of the many layers. You should have many of them, more transits. And those transits should take care of history. Well, there is a very simple model for a time which is not linear. Time should not be linear because there are a lot of ramifications in history, things which have been developed, some others which have been forgotten, some others which have been reinterpreted. So the model on the bottom part should be a time which is ramified and which also could have some comebacks to the past. If it's ramified to the future, that will be captured by what's called the Kripke model for intuitionism. And it is if it's ramified for the going to the past, then you will come back to the past, and then you have modalities. So this was presented yesterday by Clarice Mare. So I will not go on to that. Thanks for that. Here we have on the bottom part the Kripke model for intuitionism here drawn. But it could be drawn also for a modal logic in which you have the problem of interpretation to the past. Finally, history is not static. History is changing all the time, and interpretations of history have to be taken care in our understanding. But already with this, then we get some kind of understanding of the phenomenology and some kind of understanding of the history. What about the other layers? This is just using shifts. I have not used anything more. Shifts over a Kripke model. But now I will extend that with one of the greatest ideas of the 20th century, which is so simple, so profound. The idea of the topos of Goethe. What is the topos? topos of Grothendieck is a topological space, let's say beginning with that, topological space in the usual analytical perspective, in which you have some classes of open sets and points, and you want to understand that topological space. So what do you begin to do? You take one perspective, other perspective, those are called shifts. Take perspectives, shifts over the topological space. So from one, you go to the multiplicity of shifts. But then, Grothendieck observed, you take all those shifts together, that gives you a new structure that's called a topos. And that's it, there is no more. A topos is just a category of shifts over the idea of a topological space. The topological space is done analytically, you can do it synthetically. That's called a Grothendieck topology, extremely easy to define. The same actions for the Grothendieck topology, for the topology and in an analytical way, are translated in arrows, and that gives you a Grothendieck topology. If you take a category with a Grothendieck topology and all the shifts over that category with a Grothendieck topology, that is called the site, if you take the site the category with the topology, and then all the shifts over the site, that gives you the topos. That is the definition of a Grothendieck topos. That's it, there's no more. It's a very, very simple definition, which goes from the particular to the many and to the one afterwards. But what happens there is something extremely different of what was here. In this process emerges a structure in the Grothendieck topos which was not present in the topological base. That's the great discovery of Grothendieck. It has a lot of force, a lot of very beautiful mathematical force that was not here. For example, the idea of completeness. All the limits will be living there in the Grothendieck topos. Good logics will be there, what is called the subvergent classifier. There is a lot of richness, logical, algebraic, topological, geometrical, set theoretical in the topos, in the Grothendieck topos. And the diagram that you should remember is this one, which is extremely simple. You have at the bottom part a score, and then you have the instruments. Each one, the violin, the flute, etc., which reads the score. And then you have the director who makes music. The music was not in the score. Music is not on the violin. Music begins to be understood and heard thanks to the combination of all the things and the view and the ear of the director, which connects everything. That happens. It's a very big. That's why I put this movement, the movement of the conductor of the orchestra. You have the conductor of the orchestra, and it makes something entirely new, which was not in the score, and which is fundamental for the understanding of music. The interpretation is fundamental. So this is it. Topos is one of the simplest constructions of the 20th century. It was very, very in the depth, in the very deep things. They are there. Thanks to the toposes, you prove the most important problem of the 1950s, the Weil conjectures. And perhaps, we don't know, but perhaps in the future, thanks to the arithmetic side of Kohn, it will be proved the Riemann zeta function, the most important problem of mathematics by far, because it has a lot of consequences everywhere. That is a topos. So my third step. The first step was just to understand very simply that mathematics is a thought. It's not a technique, it's not vague ideas, it's a thought in which the technique and the ideas are connected. The second one, we have to move that in history. So you take shifts over a Kripke model. And the third one, very natural, you take all the shifts, all the possible shifts. Then you get this third level. You have the 1, 2, 3, that's Perse, of course. I am a Persian, I have worked on Perse 30 years of my life, so Perse, it's inevitably behind everything that we can say. I have been very happy to see that Perse is still very alive in many of the presentations by young people, very good. So here we have the toposes of shifts over KPK models, and that gives you a unity of the beyond the diversity. That unity beyond the diversity is one of the things that I want, because you have now phenomenology, you have history, and now appears the metaphysics. At the level of the topos, you have the metaphysics, because in the topos you have the archetypes which are projected onto the types. In the universal structure of the topos appear the real, profound, and deep things that were not visible on the types. So we are beginning to take care of these three levels at least. And the other one of the culture will be putting beyond the archetypes that were, in a sense, captured by the topos, how those are ramified on culture. Is it possible? Yes, it is possible again, thanks to our master Riemann. So this is like other diagrams of these ideas. Kripke model, shifts, toposes, and those correspond to history, phenomenology, and metaphysics. And you can be very careful about the internal and external constructions, the obstructions and the transits. I will show you some of the work done very quickly because we have no time. Here, for example, some examples. I have worked a lot on the last 10 years on this with a lot of examples. Some of them are examples which have been fundamental for the understanding of modern mathematics. First of all, the ambiguity theory by Galois. Galois, the young mathematician, which should be, for all of you, like the ideal, the fantastic, revolutionary ideal of a great mathematician, a great person, a little crazy also, because he was stupid enough that he committed suicide by love. That happens at 20 years. It's a pity because he would have been a fantastic mathematician even after what he did. So in only 2 years, he invented ambiguity theory. Ambiguity theory is something very simple to state. If you are interested in a structure, you need that structure should be plastic, that it should have enough automorphism. The structure can be transformed through many automorphisms. And Galois had this discovery, very simple and very beautiful discovery, that to understand the structure, you have to understand its Galois group of automorphisms. Very simple idea, but then you need ambiguity. You need to have enough automorphisms. If the structure is rigid, you will have only the identity, and the identity doesn't say anything about anything. No interest in identity, as has been well shown in the course by Gomez and Octaviano. Identity doesn't make very much sense, it's not very interesting. On the contrary, what is beyond identity, ambiguity, as Galois observed, is the key construction. And then you can construct the topos of shifts or ambiguity. There are the details, I will not go over them. The different technical constructions of Galois at the bottom, the basic ideas in the fibers, how these basic ideas are connected between them, etc., etc. Between 1830 and 1832, only 2 years after that changed modern mathematics. And then you have the complexification theory by Riemann. A little more, no? Between 1851 and 1859, it's still very little, 10 years. But in 10 years, what Riemann did is something completely amazing also. So he invented all these beautiful constructions, the Riemann surfaces, the differential varieties, our fundamental theorem at the beginning of this course, the Riemann-Roch theorem. Extremely easy, remember, extremely easy to present. Two different ways to understand the invariants, the archetypes of the surface. Going inside, going outside, okay? Riemann-Roch. Analytic continuation. The great analytic continuation will permit the construction of the Riemann zeta function, etc. And you can continue with a lot of mathematicians in this way, in which if you do it carefully, the different mathematical constructions, the idea is to go carefully on the bottom part first, the phenomenological part first. You make a good description of the mathematics which is done by these great mathematicians. Then you take the fundamental ideas beyond them, and then you connect them. And with little and little perspective, then you will get to the fundamental core of the contributions. So as ambiguity was the key contribution by Galois, complexification, the key contribution by Riemann, the key contribution by Grothendieck is to look for softness everywhere. Not only in topology, the angel should be everywhere. The angel is everywhere for Grothendieck. And you can do that with a lot of examples. This is done pretty carefully in my book, Modelos Enlaces para el Pensamiento Matemático, shift models for mathematical thought. That you can get it in my page in academia, but it is also circulating here in the Play library. Afterwards, you can go to the next level. We have an idea of what is the level of phenomenon, history, metaphysics, how is that ramified into the culture. You can get these basic archetypes that the model provides you and look how they are reflected into the culture. This is the basic diagram, in which you have the three first levels, K, S, T, Kripke models, shifts, toposes, and then on top of that, you get a Riemann surface, which ramifies the archetypes that were found at the level of the topos. And with that, you get enough connections with culture. I have done that, a lot of exercises also on that, on this very simple idea again. These ideas are extremely simple. And that's the only hope that I have, that they may be correct. They are very, very simple. After you get a level of archetype at the top of the level, then you begin to ramify it on the culture. For example, here, literature, in arts, music, in cinema, etc. I have done also all the exercises. I will not go into the details. But here, for example, how Galois is reflected in very natural way in Turner, Hugo, or Liszt, how Riemann is reflected in Novalis, Beethoven, or Rodin, Proust, Ives, Picasso for Grothendieck, etc., etc. You can do that with a lot of examples with pretty careful analysis, in which you make the correspondences in a very sound and natural way. Since they are natural, they may be correct. These are not the only one. There are a lot of other possibilities. So, for that, before continuing, I will stop here for my first part, the use of shifts, toposes, Kripke models, and Riemann surfaces to understand these four layers, these four fundamental layers that we should try to unify in some sense. And what I am trying to show you here is that I am using tools from mathematics, not only tools from logic. Tools from logic are extremely useful, but they are a part, and I insist, and I will always insist, a small part, a very small part, very interesting, but very small part. I can't say so because I am a logician. I can't say so. Very small part of mathematics. Extremely interesting, but very small. If you are interested in trying to approach mathematics, you should use other tools, which are not just logical. And here I am using tools which come from topology, from category theory, from shifts. Different tools, different mathematical tools to understand mathematics, and then with that, with the hope, which may be completely wrong, with the hope, but is the Newton, the Costa hope, that we can understand better knowledge. For him, the important goal was to understand knowledge. For me, in part, I don't have that vision, that capacity, but it's my goal also, to approach an understanding of knowledge in general. And for that, I am trying to use strong mathematical tools. So before I go to the other perspective, I want to mention, at least very briefly, that this can be reversed in a very beautiful way. Instead of taking, like here, the level of the Kripke model, the shifts and the topos, and then take a Riemann surface over the topos, you could do it the other way. You put the Riemann surface at the bottom, and then you take the topos of shifts over the Riemann surface. That produces wonderful problems of logic, wonderful problems of logic. Using Peirce again. Peirce invented something very beautiful that I mentioned briefly, but I will mention it again. Using just the plane, and in the plane making diagrams, cuts, and lines of identity, Peirce was able to produce, with the same rules, axiomatizations for propositional calculus, intuitionistical calculus, modal logics, and first-order logic, with the same rules. It doesn't appear in any other system of logic. It's the only system in which the same rules produce different axiomatizations just with the small changes of language. So beyond the language, what is important are the rules. And the rules are topological universal rules, which permit to understand the diversity. I know that many of you young people have worked a lot on Hilbert systems. I have seen a lot of the posters. And I know that you have suffered with the Hilbert systems. It's inevitable. The Hilbert systems are extremely good in a technical analytical way, but they hide what is important. What is important are the rules, the topological rules, which are hidden beyond. And Peirce, between 1895 and 1905, was able to produce those rules, to produce that calculus, and to show that unity of the diverse logics. In fact, he invented modal logics in an axiomatic way well before Lukasiewicz and things like that. First, then, you take the plane and you have a logic. Now, what if instead of looking at the plane, you look at other surfaces? Not the plane, but other interesting surfaces, the sphere or the torus. Those are Riemann surfaces. Riemann surface, the plane is of course a Riemann surface, but then you have also the sphere or you have the torus. Those are Riemann surfaces. What about if you begin to study the logic of those Riemann surfaces? That can be done, that has been done by my student Angie, who is here in this meeting. You can approach her in some moment. And she has shown something very beautiful, that if you change the surfaces, the logic changes a lot. And there is a beautiful conjecture, not yet proven, but seems to be correct, that the logic of the sphere is paraconsistent. The logic of the plane is classical or intuitionistic. The logic of the sphere is paraconsistent. The logic of the torus is a logic with 3 different negations. The logic of a surface with many holes is a logic with 3n negations, etc., etc. And that is studied using the topos of shifts over the Riemann surface. In the topos of shift over the Riemann surface, you get the logic on the top. And it's extremely beautiful, extremely amazing. It's an inversion of what I have presented you here. I have presented you here from the bottom to the Riemann surface. If you invert that, then you get a study of the logic, which is very, very good. So what Angie did was exactly the contrary of what I was thinking about. That's what a student should do, to think in a very different way of his teacher. She did it wonderfully, and it is presented. I can show you it here more or less quickly in a book that we have published with my students in Colombia, which is called Advances in Persian Mathematics. Advances in Persian Mathematics. The book who came 2 months ago in the Gruyter. It's called the Colombian School. That thing exists. It exists. It exists a school on Perth in Colombia for already 30 years. And my students have done things which are completely amazing. My only merit is to have induced them to work. And here they are, some of them. Gustavo Arengas proved mathematically, something what is wonderful in this book, is that this burst that you have used in semiotics or philosophy or logic, etc., becomes proved.
Becomes what?
Proof. There are proofs of the basic ideas of burst. It is not anymore a philosophical architectonics. It's a mathematical architecture with proofs. We have proved the main things about the system. Arengas has proved the famous pragmaticist maxim, but that was one of the dreams of Peirce. Can you prove the pragmaticist maxim in which, if you have a sign, how do you understand the sign? Through its representations, and these representations in different contexts. How you integrate these different representations in different contexts, it should give you the understanding of the sign. That is a maxim from semiotics and philosophy. It can be mathematized, and Arengas proved it for the first time after Peirce. Vargas did something incredible, which is a construction of a model for the Peirce's continuum. Peirce's continuum is something which goes well beyond Cantor, well beyond Brouwer, well beyond the other constructions of the continuum in the 19th and 20th century. Peirce had the idea of something which is very, very big, a continuum which is very, very big, and which goes beyond any multitude. It's called the supermultitudinous of Peirce's continuum, in which points disappear, you don't have any more points, and in which you have naturally all the modalities. Is that possible, to have a model gigantic, in which there are no more points, and in which you have all the modalities? Yes, you can produce the model and prove everything in that model. Vargas did it against all Persians. No Persian believed that it was possible, beginning by me. I always said to Francisco, what you are doing doesn't make sense, it's impossible. Go against your professor. Great, that's the idea. He proved it, and it's settled for once and for all. Peirce's continuum exists. It has a beautiful model, an incredible model in which you don't need all the usual analytical construction. Ostra, also another of my great students, invented the idea of intuitionistic existential graphs, and extended them to surfaces. And then Angie has worked on the extension of those works to the topos of ships over Hilke models. So we have here, you can, it is available, this PDF, just write me if you are interested, see if you are one of the persons here in the room. If not, also, it's interesting. You don't have to be present. Well, I will finish in 10 minutes, talking very briefly about the other things that I have been exploring in the last 5 years. Which is this idea, which is also extremely simple and extremely basic, that we should have something called mathematical criticism, in which the object of the work is extremely simple. Mathematics is a creation. There are a lot of works created by mathematicians. We have to read them and understand them. That's it, no more. That doesn't happen usually in the philosophy of mathematics, unfortunately, because in the philosophy of mathematics, you can, in one moment, take the basic ideas of what are happening in mathematics, then stay at the level of the concepts, and then do a very difficult and profound study of the concepts of the philosophy which emerge from mathematics. But there the mathematics disappear. This never appears in a treatise of philosophy of mathematics. So those are mathematics. You have to look at them. You cannot escape mathematics. So that's my goal and my simple idea. Let's accept that mathematics is one of the creations of the human mind, one of the great creations of the human mind, at the same level, or more perhaps, no, but at least at the same level of literature, art, film, music, etc. So there should be something called mathematical criticism, in which you look at the works and you do a careful analysis of the works, very careful analysis of the works. Very different from the transform analytical philosophy. The method is the same, but then you are looking to the mathematics with very powerful analytical weapons and instruments, but really looking at the mathematics. You cannot escape from that. And for that, I did the exercise to look at some of the masters. This is one of the masters, Bachtin, in literary criticism, but there was a very steady German tradition of criticism. Avi Warburg, I presented him in the first session on art criticism. Walter Benjamin, the greatest critic in general of the 20th century, and not just literary critic. Heinrich Schenker in music, or Siegfried Kracauer in film, etc. Some of these are some of the masters of criticism, of the German criticism, in the first half of the 20th century. So I did the exercise to read them more or less carefully, and then go to the basics of their ideas. And the basics of their ideas can be shown here. These are some of the basic ideas of these great critics. The idea of oscillation, fundamental in Warburg. I began my sessions with Warburg's pendulum. The oscillation, fundamental for Warburg, in which there is the oscillation between the antique art and the Renaissance art, and the going back and forth between them makes a study of how the Renaissance people took the antique ideas and how they changed the transformation of the antique. The residuation is the basic idea of Walter Benjamin. To understand the 19th century Paris, and Benjamin did something very beautiful. He went to the arcades, which are kind of passages in Paris in which many things are sold of second or third hand. And with the idea of taking a look, a very careful look to the ruins and the residues, he tried to reconstruct a complete image of Paris in the 19th century through its ruins, through its residues. Integration is the basic idea of Schenker, that you have a basic ersatz, and from that basic ersatz, then you have many layers which produce the construction of the score. Fluxion, basic idea in film, the idea of going back and forth between the images. And there are other things which are not related to them, but which are, I think, pretty important for me. The idea of marginalization, for example. Margins, the border. For me, it has always been fundamental. And not only because it's one of the key parts of understanding of culture, the idea of the border, but for me most especially because I live in the border. I am a Latin American, and I like Latin America. I love Latin America. And I see that from the border, things can be done that cannot be done and cannot be understood from the center. There are many things that we are doing in Latin America. One good, very good example, of course, the invention of the paraconsistent school. Very, very good thing that doing it in Brazil here and in other borders of the world, not necessarily on the center of the world, has produced beautiful things. And so on and so forth. These ideas then, who come from critics, great critics, German critics, Latin American critics, Russian critics, etc., can be translated into mathematics. The idea of marching into a border, the idea of oscillation as a pendulum between the discrete and the continuous, the idea of residuation as a real residue in complex theory, complex function theory, the idea of immersion in something which is singular thanks to the poles, the idea of fluxion as a harmonics between the positive and the negative, etc., etc. And then you can do which I call the main injection then of cultural criticism into what could be mathematical criticism, which is at the left, the great ideas of the cultural critics, at the right, the fundamental mathematical constructions that correspond to their ideas. And what is mathematical criticism afterwards? It becomes something like this. You have on one plane the basic ideas, and then you have the fibers over them. For example, in one, you have the singularities, the idea of singularity. If you go through that to Poincaré, then you get to the errors, to non-definitions, to the poles, etc. I will not do all of them. Lisura is softness. If you take the softness part, then you go to the proofs, definitions, zeros, etc. If you go to the structures, what are the basic structures? If you go to Bourbaki, the three main structures of Bourbaki, topology, algebra, and order, etc. So you have very natural fibers over the plane. And what is mathematical criticism? To understand the connections between the fibers. It can be done, and it is easily done. Here is an example in which you have most of the most important constructions of modern and contemporary mathematics shown as sections between fibers over a plane of mathematical criticism. And this can be continued and continued so forth. Beyond the basic things which came from the German masters, you can go to the second masters, the Lorenzo, Shaw, Russell, Costa, the ones that are mentioned there. You go to them, that gives you more fibers. Form, function, an idea, the notions, the mixtures, the blind points, the style, they live in a plane. You ramify them, you take the fibers, that gives you a richness some kind of richness on top. And then you want to connect the different richness. That gives you, again, a very nice understanding of what is happening in mathematics. The different sections between fibers projected on different planes. We'll be finishing with 2 or 3 more diagrams in which this becomes very, very analytically done. I am a fan of analysis, but you have to go to analysis and to synthesis and to the medium part. The 3 things are fundamental. So I have done here the exercise with Galois, with Galois' ambiguity theory, with 3 levels. The first level, which is very general archetypical level, in which you have the main ideas of Galois connected, the sections show some connections between the ideas of Galois. Then you go to a lesser level, in which you have what is called the basic Galois correspondence, and you go to the ideas which are behind the Galois correspondence, and you get a little more connections. Here, the connections were vague. Here, they become more connected, etc., etc. You can continue in that way. You can work, for example, here with the finite Galois fields and see what is happening, what are the ideas are on the top, and how are they connected, etc., etc. What I want to show first, before finishing, is very quickly, just from the picture, what you are seeing there is some kind of, at the bottom letter, some keys of a piano. And beyond that keys, on the top, you have some kind of a score. That score is saying something about the mathematics of Galois. I am beginning to call this the music of shifts. Not the music of spheres by Plato, but the music of shifts. Something very beautiful that perhaps will explain part of the development of modern mathematics. These kind of drawings are different for each one, for Galois, for Riemann, for Grothendieck, for Hilbert, etc., and you can compare them. The sections are very different, and they show what is important in their work. So you are really doing mathematical criticism. You are detecting what are the powerful forces of their work and how they can be differed and understood, thanks to this general apparatus, which becomes at a certain moment almost mechanical. In general, you can take, I cannot see very well here, but you see more or less that in the red parts, you are producing some kind of soft connections between ideas. In some of the masters, here I have put the exercise on Riemann, Hilbert, and Grothendieck. You will have these slides, and then you can go with time on each of them. Go to this. What is he saying here? What is this strange diagram? That strange diagram is saying something which is trying to capture this kind of the depth ideas of each of these great mathematicians. So I will stop here. Thanks.
Fortunately, we have only a few minutes for questions, but please.
Okay, so since the beginning of your talk, I have been thinking a lot about that. What you're saying is deeply related to dialectics, the Hegelian sense. And I have always thought about dialectics as something that could be formalized in somewhat a language which moves through time, you know, because it's language unfolding itself, you know. So my question actually would be, do you think that I'm correct? And if so, and if so, yes, I think that there might. Yeah, no, but I think that what you just showed might be a formalization to William logic, which would be very fascinating. And I have seen some other works related to that. Loffredo, for instance, which use cohesive categories and other stuff, which is related to modal logic by its turn. So yeah, I just would like to see to know what you think.
Okay, entirely correct. As Itala was mentioning, yes, your dialectics is fundamental here, and it was very well stressed by Da Costa. Okay. Again, look at Da Costa's film. He insists several times that one of his goals was to understand dialectics and try to formalize in a part that wonderful way of thought. So the idea is correct. Behind this, there is a strong dialectics. The desire of formalizing it is part of the goal, because I am not trying. My goal is not to formalize completely the construction, but yes, to explain what we were calling yesterday the informal rigor. Here there is an informal rigor. It is not formalized, it is not proved, but it shows things. It shows a lot of things. So that's something which is very interesting for me, and much better mathematized and formalized by Loffredo. Loffredo really did very good mathematics with that. I am not doing good mathematics. What I am doing is using mathematics to understand mathematics.
We have only Evandro. Could you speak it here? Evandro, you, Carnielli, and then we close because we have to finish, unfortunately.
So much, Zalamea. Thank you very much for this course. When you were disposing, I was remembering some of Milton da Costa's sayings in classes, and he always insists that he has did everything that he has did in mathematics, logic, and philosophy was seeking for beauty. Yeah.
Right. I love that, as I love many of the sayings of Da Costa, so that's why I consider him really a master of all of us, a master of Latin American logic, but more than that, a master of thought in the 20th century. He really went beyond a lot of things. And he insisted also, I didn't mention it, but in the film and several times, he insists a lot of times on the importance of criticism. A very sound criticism is for him fundamental. And this is part of what I am trying to do. Take seriously the great critics from the other fields and try to bring them to mathematics.
Could you come? Yeah, you speak.
From a naive perspective, the classical cultural criticism emerged from the fact that art implies, some mediation with audience. An audience might not be accustomed with what art is, how to perceive it, and so on. And that's why you need someone to explain, someone to analyze. And I guess the critics of mathematics are mostly mathematics because they run journals, they run conferences, and they argue with each other. And is there any audience besides mathematicians for which we need some special critic? And does critic need not to be from mathematical society? Maybe he needs to be outside because all the art critics were not artists.
Yes, extremely good question, and in fact, you are pointing to some of the most important issues there. First of all, the critic of mathematics, if that thing will be constructed in the future, does not need to be a mathematician, but does need to know mathematics. Those are some examples. For example, Lotman was not a mathematician, and for me is the best mathematical critic who ever existed. So you can be outside, but you have to look at the mathematics. It's exactly the same example that happens in the other criticism. A literary critic doesn't have, and usually is not a novelist. Usually is not a poet. He looks to the novels and the poetry from outside, and he sees things much better sometimes, or most of the times, than the novelist or the poet. Most of the times, the literary critic sees more. That happens very, very clearly with art criticism. In art criticism, the art critic shows a lot of things that the very artist doesn't see. So that's one of my goals, to produce this kind of knowledge, which I would call mathematical criticism, which would be systematic. That's my point. That's in which the thing that I am interested. Not just to have a feeling, but to have a system. That's why I am insisting on shears, on the fibers, on everything, because there is a system which helps.
Okay, the last comment, my colleague, Dr. Carnielli, please.
Thank you, Fernando, for this very nice collection of lectures and from your romanticism, by taking mathematics and logic back to the romantics. I have a sort of a technical question, but it's not only a question, it's more sort of criticism. Okay, you have put some good emphasis on shifts, right? And trying to show how shift theory shows this big wave of mathematical movement, to which I agree, but there is in particular one, you also emphasize the topos theory. And I myself and some other colleagues, we tried to study topos theory, naively thinking that they would give us a kind of very universal clues to extend to logic and blah, 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 blah. And unfortunately, topos theory sort of tight closer into the binary thinking. So because of this sub-objective classifier, and because they are always talking about the internal logic of topos, is intuitionistic logic. But we thought, how can we do that? Why can we go besides that? Why can we generalize that? So, in my opinion, topos theory is sort of it's just a pedantic way of talking about the intuitionistic logic, and not about logic in general. It does not give us this kind of big movement. And we should try to do something else. And so I'd like to hear what you have to say about it.
Okay, great criticism, beautiful. The first point is that topos theory were invented to solve strong mathematical problems. That's the point of topos theory. Topos theory was invented to solve the veil conjectures, and it worked very well. That was the main goal. And with that, there was a new understanding of space and number, and there is this expectation that it may hope to solve Riemann-Zeta's problem, which are very, very important mathematical problems. On top of that, there is this emergence of logics inside the topos. Grothendieck was not thinking about that. That came afterwards with Bromir and the school of elementary toposes and things like that. But it is also true that in a general elementary toposes, the logics are very wide. They cover also intuitionistic logics, at least. So on the side of Boolean algebras to the Hating algebras, you have all the possibilities. If you are interested in the other part, in the paraconsistent part, the way to look is to look at cohating algebras, the complements. And in those cohating algebras, there could be, perhaps, I don't know if it has been done or not, but it seems natural
Coherent algebra?
Cohesive.
Yes, dual.
Yeah.
Yes.
Yes.
The algebraic structure is associated.
And then there are
to
toposes in
logical
which
and
the
general
algebra
dual.
is at the same time hating and cohating. And
We call dual.
dual. Loffredo studied them and they invented the idea of cohating algebras in toposes. And in principle, that should be applied. That could be applied to Parallel system.
Yeah, there's no this kind of very clear connection between the duality. Between
No,
parallel
But
probably
we
it
have
did not, but
studied several algebraic structures associated to parallel-consistent logics, and we have shown that they are kind of dual algebras.
Yeah,
Yeah.
partly,
Yeah.
yes.
Yeah.
Yes. My student, your Andreas.
But we know with Andreas, we proved that the connection is not well done.
Oh,
Yeah,
probably there is still time to be done, but
There are some
in
steps,
principle, it should be possible to be done. I don't think that the idea that toposes are classical, no, they go well beyond the classical world.
Thank you. So, Professor Zalamea, we would like to thank you very, very much. Thank you for having come, for being participating in this school. We are very proud
I am extremely happy to be here and it
because
was
you have
very
come,
interesting.
and thank you for your course. So, so provocative, instigating, and inspiring course.
Thanks,
We
you're
thank you
very
very
kind.
much.
Thank you.